so for most problems, if you need to find a maximum or minimum, relative maximum or minimum, you're going to be able to take the first derivative, like we've already done, make a sign line, tell where it changes from positive to negative. That is what I use primarily for finding maximums and minimums. However, the second derivative test is another way that we can find maximums and minimums. And you do have to know it because AP will ask you some questions, and I'll show you a few here in a minute, where you can't do it using the first derivative test, where you have to use the second derivative test. So, the second derivative test, for the second derivative test, you are first going to find when f prime of c equals 0. What are those? What are those points called when the derivative equals 0? Not points of inflection, critical points. No, I did not say double. Just a single prime here. So, if we know we're at a critical point, so we still have to know that the first derivative is equal to 0. So if we know we are at a critical point, then if we look at the second derivative, if the second derivative is positive, so f double prime of c is greater than 0, that tells us that that really should say f of x is concave up at c. So f of c would be a minimum, because if we're at a critical point, we know the derivative is 0. So if we're concave up and we have a derivative that is 0, we have to have a minimum point. You got to be a little careful with this, because concave up makes me think maximum. Up and maximum seem to go together in my mind, but they do not. If you're concave up, you have a minimum. So that's why a lot of times I'll draw myself a picture. If this is concave up, it's going to have a minimum. Okay? It is another way. So sometimes you could use either. AP will ask you some questions where you only have limited information, where you have to use this. Yeah. And I'll show you what those look like here in a minute. So f double prime is less than 0. That tells you you're concave down. If you're concave down, your critical point is a maximum. If, for some reason, your second derivative equals 0, that's neither positive nor negative, so the test fails, and you would have to use the first derivative test, which means you would have to make the sign line like we have been doing all along anyway. So that does occasionally happen. All right, so the first derivative test is when you take the first derivative, you set it equal to 0, and then you make that line where you decide whether it's positive or negative, and decide whether it's maximum or minimum there. So this is another way of finding those maximum and minimum points. So the first three we're going to do are ones that you could do using the first derivative test. So if you see a problem like this and you prefer the first derivative test, you're perfectly welcome to use the first derivative test, except on tonight's homework when I want you practicing the second derivative test, obviously, right? So you are still going to take the first derivative. This one's a pretty simple first derivative. You are still going to set said first derivative equal to 0. So we'll get 2x equals 6 and x equals 3 here. So that is our critical point. Not necessarily. C is just a variable, a constant. I think because they're talking about a specific point there. Yeah, but I probably was pulling that from somewhere. What you got, Coach Wood? Alright, so it's just a random Coachwood visit. This happens sometimes. At least he didn't hit you. He did lightly, but I think it was more. Yeah. Should we charge him? Maybe. I would maybe address it. All right. So. All right. So this is our critical point. Instead of making our sign line, which we could do and find the maximum here, it tells us to use the second derivative test. So now we are going to take our second derivative, which is 2. And so 2 is positive here. We don't even have to plug numbers in for this. 2's always positive, right? So if we found f double prime of 3, we'd still get 2 because there's no number to plug in there, which is greater than 0. This is positive. So if my second derivative is positive, that tells me that I'm concave up, and that means I've got a minimum point. I always draw my little picture because it's easy to get that mixed up. Positive is increasing when we're talking about first derivative, but positive is minimum when we're talking about second derivative tests, which to me is a little bit backwards.
Is a good way to remember it, like concave up has the U for up, and concave down has the in for...
Yeah, that would actually be good. Yeah, so here we will say that F has a relative minimum at x equals 3 because f prime of 3 equals 0 and f double prime of 3 is greater than 0. So when you're justifying this with the words, this part right here is always going to be a given. The first derivative has to be 0. If it's not, then you're doing something terribly wrong anyway. So first derivative has to be 0. And then the second derivative, you're telling whether or not it's positive or negative there. And you want to do f prime of 3 and f double prime of 3, not f prime of x or f double prime of x, because it's at this specific point.
When you said the first derivative has to be 0, where is that? You mean like a set equal?
So that's where we set it equal to 0 and solved. Yes.
Oh, okay.
Yeah, so that first derivative, if the first derivative doesn't equal 0, we wouldn't even be considering that point for the second derivative. So now, you might prefer second derivative test to first derivative test. If you like it better, you can start using this instead of first derivative test for a lot of them. I don't necessarily think it's easier, but I think it's just as easy when you're doing a problem like this. I don't like using it whenever you have a difficult second derivative to take, because if you've got to do like a quotient rule with a chain rule inside of it, then I'd much rather just take the derivative one time. But a simple derivative like this is not so bad. All right, so let's do another one. Okay, same thing. I didn't specifically say use second derivative test, but use second derivative test. So this one, also not too terrible, a little tougher than the last one, but it's not too terrible because we can take the derivative of this twice pretty easily. So if I take the first derivative, Luis, what will I get for my first derivative here? Good. And so, first derivative, I'm going to set that equal to 0. I'm going to factor here. Let's see. 3x and 2x minus what's it going to be? Somebody beat me to this. Minus 4 here, plus 1 here. Yeah, that'll do it. So that'll give us a negative 8 in the middle. The outer terms are a positive 3. That gives us our negative 5 that we need. This is negative 8x. And this is positive 3x, which gives you that negative 5x. Yeah. So each one of these, 3x minus 4 equals 0. So we're going to get 3x equals 4, which is x equals 4/3. And then over here, 2x plus 1 equals 0. So 2x equals negative 1, and x equals negative 1 half.
So the inside 2, 0, not finding 0.
So what we're setting the whole thing equal to 0. When you factor this, you can set each one equal to 0.
You're not finding the 0. Like, it wouldn't be 4. Well, actually, isn't that finding the 0?
These are the critical points. Critical points. Yeah. Okay? All right, so we found critical points. Now we're going to take our second derivative. And for our second derivative, Laura, what do we get? 12x minus 5. And so what I need to do is I need to test whether my second derivative is positive or negative at each one of these critical points. So f double prime of 4/3 is going to be 12 times 4/3 minus 5. That's going to be, let's see, if you reduce there, you'd have 16 minus 5, so you'll get 11. And if we do f double prime of negative 1/2, we are going to get 12 times negative 1/2 minus 5, so negative 6 minus 5, we get negative 11. So, Alfredo, if our second derivative is positive, like we have at 4/3, what's that tell us? Not that it increases. The second derivative tells us about concavity. So our function is concave up, which means we'll have a maximum or minimum. And then over here, my second derivative is negative. That tells me concave down, which means I have a maximum there. So you got to write this out in words. You got to say f has a relative minimum at x equals 4/3 because f prime of 4/3 equals 0 and f double prime of 4/3 is greater than 0. And then you'll write a similar statement for the maximum. That says f double prime of 4/3 is greater than 0. No, it cuts me off. Correct. If you wanted to add in something about concavity, you could, but this is like the bare minimum that you have to write. And you can't just say concavity, you have to tell the concavity because of the second derivative, so you might as well just say second derivative. Yes. I think it's printed on the, maybe not. Is it printed on the last page? Yes, so it is that. Yes, I will. Okay. Questions on number 2? Good luck, girls. I hope you win. Who are you guys playing? Forsyth Homeschool. Are they going to be any good? I can see it going either way there. Yeah.
Yeah, but homeschool kids, they sleep all the time. So they're not getting every homeschool person I ever met is really tall.
I'm pretty sure the height of homeschoolers is not across the board different, but could be. Coach Wood has accused the cafeteria of causing them to have bad football seasons before.
Well, that doesn't have anything to do with the cafeteria. I'm not made at the cafeteria here.
Oh, there's proof. That's further proof of our assumption, though.
No.
Logan does not eat in the cafeteria.
Never have. How would you like to face off a homeschool football team?
We need to know if.
What kind of homeschool is you talking about?
So, all right. Okay. Another time I like to use second derivative test instead of first derivative test is if they ask me for extrema and points of inflection. Because if they ask you for both, you're going to have to find the second derivative anyway. So it's not that much. You only have to make one sign line instead of 2. So sometimes I do actually prefer second derivative test on a problem like this, although you could still use first derivative test for your extrema. Right. But if you don't want to, you could still do first derivative test and then still have to find a second derivative for points of inflection. So, well, I mean, all right. So, first derivative of this, negative 15x to the 4th plus 15x squared. We're going to set that equal to 0 to find our critical points. We could factor out a 15x squared or just x squared, whatever you want to do there. Negative x squared plus 1 would equal 0. So 15x squared would equal 0, which would really just be x squared equals 0, so x equals 0. And over here, negative x squared plus 1 would equal 0. So if we move that x squared over, we got 1 equals x squared. We will square root both sides, and we will get plus or minus 1 for our x. Right. So we found our critical points. They're at 0, 1, and negative 1. At this point, we could make a sign line, use first derivative test, find maximums and minimums. But since we got to find the second derivative anyway for points of inflection, I'm going to find that second derivative. So now, negative 60x cubed plus 30x Alright, so if all I cared about was extrema, I could just plug in 0, 1, and -1 and see what I get. But I also need to know points of inflection. So I'm going to set this equal to 0. I'm going to factor out a 30x. So it'd be -2x squared plus 1. I'm going to go ahead and do points of inflection first.
Would that be x equals still? Points of inflection?
Points of inflection is still x, but you're doing this with the second derivative. Yeah. So I got 30x is 0. -2x squared plus 1 is 0. So here you're just going to get an x equals 0. Right here we'll have 1 equals 2x squared. Divide by 2. We're going to square root. So we end up with plus or minus the square root of 1/2. I don't like that, but that's what we've got. If you want to make that 1 over root 2, you can. You could even make it root 2 over 2, but I would just leave it. So let's make a sine line with our second derivative. When you make a sine line, it's best to label it so we know it's f double prime of x. So I'd have -1 over root 2. I got 0, and I got 1 over root 2. Alright, so for concavity, I need to plug a number into -60x to the third plus 30x, the second derivative. So I think instead of trying to make a chart here, I'm just going to plug that in. So like I'd plug in a -1 here, which would give me positive 60 minus 30. So I'll get a positive right there. Yeah, different way. I mean, this is the same way for concavity. Yeah, this problem is like a combination problem. It asks you how to do concavity, which we're doing like we have always done concavity. Then we're going to back up and do extrema as well. Yes, Thomas. If you want to leave it square root of 1/2, that's fine. Right, square root of 1 is 1, so you can write it 1 over root 2. Or you can leave it square root of 1/2. Either one's fine. Here's something a little tricky. Finding the value between 0 and 1 over square root of 2. So, yeah, 1/10's a pretty good idea. So, f double prime of 1/10 would be -60 times 1/10 to the third plus 30 times 1/10. If you want to use decimals, you can, but it's not calculator active. So -60 over 1,000 plus 3. But we know -60 over 1,000. Oh, wait, hold on. I'm plugging in -1/10. That changed both of my signs, so that's positive, that's negative. 6 over 100 is less than 3, so I'm going to get a negative here. But if I did this, that should have been -1/10. If I did the same thing with positive 1/10, f double prime of positive 1/10 would give me a -6 over 100 plus 3. So I'd have a positive here. If I plug in 1, I get -60 plus 30. I get a negative here. Right here, this mess. So I was just plugging in. I was picking any number between -1 over root 2 and 0. So I just went with a small fraction that I knew. I could have used anything like 1/8 or 1/5 or something, but I picked 1/10 just because 10's easy to deal with. So, yeah. Yes. Yeah. And that's all like scratch work that they don't have to see. If you could do that in your head, you can. But you don't have to do that. So for points of inflection, we would say F has points of inflection at x equals -1 over root 2, x equals 0, and x equals +1 over root 2, because f double prime of x changes signs. What? You don't have to tell concave up and down here because they only ask for points of inflection. So you can just say that the second derivative changes signs. If you added that extra information, it would be fine, but it's not required because they were only asking for points of inflection. These are points of inflection. We have not done those yet, so we still have to do those. Yeah. Yes. You can put it on a chart. The reason I didn't here is just because you got 30x and -2x squared plus 1. And to me, it just seemed easier just to plug it into that original. Right. If it's really broken apart, like especially if you have like x plus 2 times x minus 3 over x plus 5, like that I definitely use the chart for. It's just whatever you prefer as far as what, because we could have here done 30x and -2x squared plus 1, but and then seen what we got here, but I didn't, but you could if you wanted to. So, all right, that's only points of inflection. We have to know extrema as well. So, our critical points were -1, 1, and 0. So, at 1 would fall right here, right? Somewhere, I'm sorry, -1 would fall right here. It would be somewhere right here. So, second derivative, is it positive or negative there? It's positive because our chart tells us it's positive, right? You don't have to know the value, you just have to know it's positive. So, if it's positive, that tells us concave up, which means we've got a minimum. So, we'd say F has a relative minimum at x equals -1 because f prime of x, I'm sorry, f prime of -1 equals 0 and f double prime of x is greater than 0. And then for 1, it would fall over here. Our derivative is negative, our second derivative is negative, meaning we got a maximum, so f has a relative maximum at x equals 1 because f prime of 1 equals 0 and f double prime of x is less than 0. Here's the problem that makes this one that we've already spent too much time on really annoying. What is the, our other critical point here is 0. What's the second derivative at 0? 0. What happens if that happens? The test fails. At which point you'd have to go back up here and make your first derivative sign line. with -1 and 0 and 1 and do all of that and tell me what happens at 0. And we're not going to do that right now because I need to do these last 3 problems. Yeah, so I do not like second derivative test much. I usually just use first derivative test. However, here's why I've got to teach it to you, because there have been years I skipped it until I realized that problems like this show up on the test. All right, so something like this might show up. They might give you an implicitly defined function. And if they do, you can't really make a sign line because you're dealing with x's and y's. Right? It'd have to be like you'd have to do the coordinate plane and test sections of the coordinate plane, and it would get crazy complicated. So if you see something where it's implicitly defined, you're going to have to use second derivative test. So for this, if I take that second derivative, it will be -2x minus, when I take the derivative here, x times y, what have I got to use? I'm going to need that, but I also need the product rule. So x times the derivative of y, which is dy dx, plus y times the derivative of x, which is just 1, so I'm not going to write it, plus 2y dy dx, and the 1 will just be 0. So this is my second derivative. There, I'm looking at the point -1, 1. Okay? Because it gave me this piece of information right here. So, I really should have checked first. I need to know what dy dx is at -1, 1. And I'm writing right on top of the problem here. So if I plug -1, 1 in here, I got -1 squared minus -1 times 1 plus 1 squared minus 1. So that gives me -1 plus 1 plus 1 minus 1. That gives me 0. So I know the first derivative is 0. That is actually good, because if the first derivative is 0, that tells me this is a critical point. If it was not 0, then I would probably have to pick, I don't think, you'd have to pick D, I guess, if it was not 0. Or there might be an answer choice if it didn't equal 0 where it says there's neither 1 here. I guess actually maybe C, because if the critical point, if you don't get a first derivative of 0, it can't be a maximum or minimum. So I need to know now what the second derivative is at this point. So -1 minus -1. What's dy dx at this point? It's 0. So I get 2 minus 1 plus 0. So I get 1. So 1's positive, tells me concave up, gives me a minimum. So I have a minimum at x equals -1. I bubbled it for you guys this time.
Wow.
About 3 minutes, 2.5, 3 minutes. Okay, here's another one. I like these. I do like these for second derivative because there's no math to do. Okay, so it gives you a chart. It wants to know which of the following statements are true. F has neither relative minimum or maximum at 1. It has a relative maximum at 1, a relative maximum at 4. So we're going to look you can't necessarily tell because on this chart, they don't tell us they gave us all of the critical points. So, like, for example, right here, our first derivative equals 0, so that means 1 is a critical point. And the other place we have right here, our first derivative equals 0, so 4 is our other critical point. So, between 1 and 4, what's your sign of your derivative? Positive or negative? It's both. So we can't use first derivative test because they haven't given us enough information. They're only giving us like little pieces. But we can look down here at the second derivative. Second derivative tells me concave down because that's negative. Concave down at a critical point means I've got a maximum. So this is a max. Max at 1. And here, concave up, this one's going to be a minimum. So, the only one that is true is number 2. So you can see how, like, a problem like this, you have to know the second derivative test. You can't get around doing it a different way. You couldn't use, because right here, between here, I don't know if it's positive or negative if you're looking at the first derivative. So it looks like you go from negative to negative and don't have a maximum or a minimum right there if you just look at those points, because these are just selected values. So it might do other stuff in between there. Right, you can't. Yeah. Okay, last one. F is a twice differentiable function. Which of the following statements are individually sufficient to conclude that x equals 2 is the location of the absolute maximum from negative 5 to 5? Hello? Yes. Who is that? No, okay, yes. All right, thank you. When the bell rings, you're supposed to go by the office. Don't know why. Okay, so it's not A, because just knowing the derivative is 0 does not guarantee it's maximum or minimum. All right, for 2, it's the only critical point. And you know, second derivative is negative, which is a concave down, which means a maximum. So this is second derivative test. It works. All right. So, you know, it's a critical point, which tells your first derivative is 0. And the second derivative is negative, which means it's concave down, which means you would have a maximum. Yeah. So that's the possibility. All right. Here's our other possibility. Only critical point. Okay. Only critical point. Negative 5, 5. It tells you f of negative 5 is less than f of 5, which is less than f of 2. F of 2 is bigger than f of negative 5 and f of 5. So if I'm looking, and remember this is absolute. So if I'm looking for absolute maximum minimums on an interval, then I take the derivative, find the critical point, which is 2. Right? They tell us 2 is a critical point. And I test the points, 2, 5, and negative 5. Whichever one's the highest is my maximum. So this one is right also.
I didn't even read that one.
And so
I saw that. I was like, correct. I saw that. I'm like,
there's why. Yeah. Okay. So the assignment is these 6 problems here. Use the second derivative test on those as best you can. Thank you. Yes, if you get stuck, you can use the first, but try not to do it on the whole thing because we need some practice with second derivative.